All right, good morning, everyone. Thank you for joining us this morning. Hopefully the PowerPoint screen is coming through. It gives me the thumbs up, so that means, Richard, we're still working, and hopefully it continues to work so well. Before I get started into my comments here, and we'll try to be as efficient as I can, and about this work that recently came out that I had been working on for some bit of time, but also something that is just really exciting and really proud to be able to share. I shared it in the email from the SIG, but for those of you that interacted with Hector and saw the message and his big announcement on taking a position at South Dakota State University's Department of Animal Science. Couldn't be more proud of a colleague and friend right there. So again, big kudos to Dr. Menendez for landing that spot right there. And I would fully expect to see some presentations to the SIG about what he gets going in his new position down the road. So with that, I'll jump into the comments I have about this paper. The title, as you can see there, Model Laboratories, Quick Start Guide for the Design of Simulation Experiments for Dynamic Systems Models. Let me see if I can put, there we go. So where is this paper? I was able to get it through an ecological modeling. The journal information is there. Where can you find it if you don't have it through your institutional library to give you access if it's a subscriber to the journal? But there's other ways you can get it. I have it if you're on the SIG Facebook page. The author link that I posted there will give anyone access through October 8th. I also have a private copy on ResearchGate, and I've already had some people ask, and I've shared it to about it, and I can find a way to get it to you or anyone you'd like to share it with. But I prefer hopefully the author link or the ResearchGate, because the file size for the route is probably going to get kicked back. So, but ResearchGate, I can share it no problem, and it's already worked. So, so that's how we can get it. How I can get it to you, should you be interested. The overview for what I'd like to share is kind of these main sections: the scientific method for system dynamics. I'll spend the least amount of time there, but I think it's a nice foundation to lead into the rest of what I'll share. And I was trying to also think of a nice way to at least lay the foundation that I did in the paper. But if I just copy what's in the paper, it's kind of boring. And so I'll share some thoughts on that. The motivation for sort of where this thing came from, and sort of my own personal experience that led to trying to do something with this paper. And then what's actually in the paper and what I talk about and discuss and what do I provide there. And then for the model that is used, what are some future uses of that model? So just to lay the foundation for model laboratories and model experimentation, just a little foundation on the scientific method of system dynamics. So you've all probably seen, or similar schematics of this as the scientific method. And what's been so the unleashing of human creativity and innovation that harnesses the scientific method. We reduce a particular problem down into the manageable compartments that we can test. We replicate it and we repeat those experiments and try to refute a particular hypothesis that we might be testing for. And that's been an extremely powerful approach. But for everyone on this call, for that actively works in systems, we recognize that the complexity of the systems we work with often conspire against our ability to actually reduce those systems and problems down to those just single elements that we can manipulate, because it's the interactions between all those things that drive the behavior of the system. So that poses a problem for this sort of traditional scientific method. So there's been increasing recognition of that. And again, I'm preaching to the choir here because most of us work in systems and do system dynamics, but it's still relatively new enough and different enough that a lot of people still struggle to see how system dynamics or computer simulation in general really adds to the knowledge base that we have in science. So computer simulation has started to been described as the third pillar of science. The first two, and I should say these slides, I have my source down there, Dr. Rogelio Oliva at Texas A&M. I replicated a couple of his slides with permission, just because I think they do the best job of summarizing these ideas in 3 or 4 slides. So the two main pillars of science that we've leveraged are theory and experiment. And these two pillars work in tandems, and we use the experimental evidence and the observations we have to refute competing hypotheses or competing theories about how the world works. And so we ask questions like, how well does the theory explain the observations of the data? Does the theory hold water under competing ideas? And in those particular circumstances where we can reduce the system down to essential elements that we can make sense of, it's really powerful. But given the complexity and the interactions that we all are concerning ourselves with, this becomes more of a challenge. So computer simulation has now been started to describe as the third pillar of science, because if you do it well and you do it right, it can change how we learn, experiment, and theorize in these systems that are, sort of irreducibly complex. So how do we do that in terms of theory and experiment? Well, these are all terms that you're going to be familiar with, but system dynamics theory building, we concern ourselves and we represent systems in terms of stocks and flows. We try to capture the policies behind decision making. We aim for a broad model boundary to include all the necessary feedbacks. We use grounded methods, so it's more inductive and data driven. And ultimately, we use all those perspectives to build endogenous explanations of the observed phenomena in terms of the feedback dynamics that are at work. So that's kind of how we build theory. And then how do we test theory in system dynamics? Well, all of our assumptions have to be explicit in generating and building the model. We go through model calibration and all sorts of tests, which we can talk more about in a moment. And we use the model to explore and test different assumptions, different decision-making, different policies at scales that aren't accessible to the reductionist approach, because we deal oftentimes with time scales over much longer than we can do in a traditional experimental setting, and over spatial scales that are just too costly. And all those things help us assess our own mental models, the implications of how we do things, and the limitations of our thinking. So Rogelio Oliva, again, this is kind of where I've replicated this because I corresponded with him here recently, and so he was gracious enough to kind of share his ideas. And he kind of boils down doing science with system dynamics models into kind of three broad categories. Model calibration as hypothesis testing, system dynamics models as labs, and then articulating falsifiable process theories. And basically, what I'll share here in just a minute mostly falls into the second bullet point there. System dynamics models as laboratories for testing our assumptions, testing different policies, so on and so forth. It touches a little bit on process theories because I share with the reader basically walking through how to interpret what a model is doing for a change in a particular variable or test. But that's kind of where it is. I say model calibration stuff for somebody else to describe, and there's other resources out there to do that. So hopefully that's a quick enough introduction and more interesting than sort of the literature I cite and the foundational stuff in the paper. But I think sets the stage for what I'll talk about in a moment after getting through this motivation. So this is not in the paper at all, but it's just kind of some background on my own thinking and evolution that led me to try to produce this paper and frame it the way that I framed it. And so I'll walk through this bathtub model of learning, and I can already hear the alarm sirens in your own heads going off. It's the conceptual model. It's not a working model. All right. So just follow the thought process and don't give me a hard time about units and conservation and all that stuff. All right. I think you get the idea. So how do we learn? Well, if we're going to become advanced system scientists, we got to start at the beginner level if we don't have any exposure. And it takes some time to do that, but we do acquire some elementary skills. And over time, eventually we accrue beginner skill and continue to advance, and then we acquire some intermediate skill. And then ultimately, to get to where we want to be, after some more time, we acquire some advanced skill. And so these buckets can fill up at different rates because we can move on to certain things in the intermediate or advanced before we might have all of the things in a particular bucket, but I think you get the idea. So this is something, you know, as a scientist, this is what we try to do. This is our discipline, and to be contributing to it and to do the best work we can, we progress through this kind of learning chain, if you will, this progression and maturation and skill level. Now, unfortunately, we don't always remember the things that we're taught. And depending on how well we comprehend and retain what we've learned, we forget certain things along the way. We get farther away from it, and so we forget certain things. So there's some things maybe that we forget that are essential skills, beginner skills. There might be certain things we forget at the intermediate skill. So I have those two things. As we forget certain things along the way, there's undiscovered things that we have to relearn. And I kind of borrowed this concept from the project management literature where, say there's a particular project that you're going along the way, and you think you're making progress, but there's undiscovered rework where you have to go and patch up previous jobs that weren't done. Same kind of idea. So there's undiscovered need to relearn. Now, the farther we get along, the more we're able to retain those things. So I have those as kind of a balancing factor there. But what happens when we accrue stuff that we just forget about in this undiscovered need to relearn? Well, it leads to modeling errors. And actually that modeling errors down there could actually be a stock by itself, but I just, for simplification, I just have it as a variable there. But without covering all our bases and thinking about those things, and we don't incorporate that into our model, it leads to modeling errors. And then when the model error is baked into the model, and then the model does something we don't expect it to, we detect that as an error, and we discover that there's something in our learning or something that we forgot about that we have to go back and correct. Of course, the more advanced we are, we can pick up on more of those errors faster and sooner. So that's helpful. And as we clear and correct those learning defects, um, I have that going into advanced skill. Now, part of it is, again, a simplification, because if we relearn a beginner skill, it's still a beginner skill. If we relearn an intermediate skill, it's still an intermediate skill. But the advanced part about it is if I can self-diagnose the error and then correct it, that in itself is an advanced skill. To be able to find my own error and correct it is something that is more advanced than just understanding a particular stock or flow dynamic. So we correct those things as fast as our error correction rate. And when confronted with problems, we use all of our skills to try to correct that particular error. So that's kind of, my sort of conceptual model of learning and advancement. Couple of things here to point out are the non-uniform delays across the top of this learning chain, because the beginner skills in terms of understanding what a stock or a flow might be and putting that down on a model, on auxiliary, identifying a particular delay, those things people pick up on, and you can learn those things pretty quickly. It may take a little bit longer to actually use that to be able to make your own model. Sort of your own elementary beginner model may take several months using those basic skills. And then the most advanced skills takes some years. It takes a lot of practice, replication, repetition, so on and so forth to get to that particular level. So that poses a challenge for people trying to do system dynamics or systems simulation in general, because of that those non-uniform delays. So it takes longer to get to the advanced than it does the intermediate, so on and so forth. So based on my experience learning for myself, system dynamics, and now doing some teaching in system dynamics, what happens when you get down into this bottom stock of undiscovered need to relearn? And so here are some voices from my students, and if you've done some teaching yourself or you've done some self-teaching for your own self, what were you saying to yourself if you got stuck in this bottom stock of undiscovered need to relearn? Well, when confronted with some modeling errors, here's what my students often say: my model runs, but it doesn't do what it's supposed to do. And I have to remind my students constantly, the model did exactly what you told it to do. If the model screwed something up, it's because you told it to do something screwy. It's not because it's conspiring against you, to slow down your progress. It's doing what you told it to do. If it's doing something wrong, then you've got some decision rules or some errors baked in there somewhere that's making it do something that does not look right. So after some time and teasing it apart, I will start to help the student identify and detect these learning defects. Hopefully they start to come to see it for themselves. But once they detect that and sort of the scales come off the vision, so to speak, wow, now I see what I did wrong. And it's sort of a aha enlightening moment. That's not how you do that structure. That's not how you program a particular segment of a model. All right. And so that moves us then into this discovered learning defects. Now we know what's wrong. And if we can identify what that is, now we can correct it. But oftentimes what I see from students who are trying to learn and trying to get this is they get stuck in this discovered learning defects. And a voice that I hear, I sort of synthesized this: I knew what I needed to fix, but could never find a solution to the problem. Oh well. So what's going on down here in this discovered learning defects right there that leads people to basically give up to that conclusion? Well, if we draw a reference mode for discovered learning defects, if we drew a good reference mode for that, what would it look like? Well, for those that make it to the advanced level, their reference mode may look something like this. So over time, as they're developing their skills, developing their models, they're going to identify areas where they've got to get corrected. And so the discovered learning defects go up. But as those things get corrected, they clear that stock, and now that's no longer a problem. So they're finding errors, they're correcting errors. Once they get their correction in line, they bring their model and learning defects back down. So this might be something that looks like those people that make it to the advanced stock. They're identifying those things, and then they're clearing and retaining those improvements. What about someone who gets stuck at the beginner or intermediate level? They've identified these things in their model and their own thinking about how to or what's going on that's wrong, but they can't get it fixed. They can't get it corrected. So they know there's what's wrong, but they haven't cleared and corrected those errors. So that gap in between what they see as people that are making progress and leveraging the power of system dynamics or system simulation, but they haven't reached that. Well, the longer they're there, the more frustrated and fatigued they get with trying to get it fixed. So that poses a challenge. So if we back up to this learning model again, this is where I see most people give up, because even if they value and appreciate and really gravitate towards the power of systems, they just simply kind of become apathetic and kind of give up because, you know, I just couldn't get it there. I knew there were some issues, but I just couldn't get it fixed. I couldn't overcome the hurdles that I had. So in terms of leverage to clear that stock, where can we look for potential leverage? Well, there's several places as I see it on the schematic. We can avoid model errors down there on the bottom. We can avoid those guys. We can potentially shorten the delay from getting us from beginner to the advanced skill level so that we can identify and clear those errors faster, or we can accelerate the error correction rate. So those are three possible ways to help clear that stock down there a little bit faster, to move people along their learning and skill level. So, but there's some issues with each one of those. So shortening the delays, this is the most expensive option. So learning system dynamics by the seat of your pants, as I had to learn it, inevitably creates longer delays, but even in the best programs, delays are a part of learning. And I put the dollar signs there because they're costly. To take the classes, enroll in the programs, you know, do all that stuff, a lot of time, a lot of resources to do that, to get that coaching and expertise that we need. We could generate it ourselves, it just maybe takes a little bit longer. And learning is inevitably a longer term process. We could avoid model errors, the error rate, and to alleviate that, we need good model development. And I think, just my opinion, is the field, I think, is pretty well saturated with good model development resources in terms of the textbooks and chapters and papers and teaching material and so on and so forth. There's pretty good saturation of model development resources, but without proportional process help in testing and experimentation, novice modelers may be left hanging. And as I have, you know, gone about business these several years and looked for the best resources on model experimentation, most of the time an experiment or a test is described, and to do the application, we just cite other people's work. Look at how this person did that, or how this person did this. And so we end up with these applications that are spread all over the literature. So simply citing other people's applications is not always helpful, because we don't have time to hunt down all those resources, understand how they did, and then there's different programming languages, and what decade was it done in, and you know, all those things make it kind of a challenge. So that's where I kind of pinpoint the accelerating correction rate, which is what my paper is all about. Good model analysis and interpretation. The prerequisite for that is good model experimentation. here's the problem or the challenge, as I kind of surveyed the world, the literature in the world about this, is the technical, theoretical, and methodological advances are often inaccessible to non-experts, and they're most often demonstrated on small models of well-known dynamics. So they're demonstrated on models where we know kind of the core dynamic, a basic project management model, or a diffusion innovation type model, or the World 3 or the urban model. The models where we know kind of what the core dynamics are, leaving us applied scientists hanging, because if you're like someone like me who's doing, we're not studying general system dynamics for, what all those cases I just mentioned were, we're building novel, new models for, management cases that, we don't know what the underlying dynamics are yet. So we're doing novel applications, and the dynamics are emerging. We don't know what they are yet, so we're building more elaborate models that are trying to capture the real world issues that we're currently working in. But as I see it, if we can accelerate the correction rate and build that expertise sooner, it does shorten the delay for somebody. If you're like me and you're mostly self-taught in system dynamics, then that can shorten the delay. If there's resources available to package these things and to accelerate how someone could test their model, interpret their model, correct a particular issue, and keep moving forward, the faster that is, then for the self-taught and for the self-trained, that will hopefully shorten the delay. So what if there are resources, a resource to bridge the gap for beginning modelers? That was kind of my hope for the paper. And so it demonstrates a range of tests that I'll get to. I provide the theoretical background, but most of the focus is on practical examples without the need for searching far and wide in the literature for what people are citing for different tests. One that helps move novices from model developers, where we're most comfortable sooner, to model experimenters, where we often struggle. What test should I do? How do I do it? So on and so forth. One that includes the model and all the supporting documents with no requirement for programming outside of ordinary system dynamics. I've asterisked that one because I need to come back to it on a subsequent slide there. And one that would have accelerated my own capabilities, because as someone who was mostly pretty much self-trained, self-taught, I had some mentors along the way, of course, but most of the technical stuff I just had to learn somehow. And to have something that would have accelerated all that is something I hope to produce. So what's actually in the paper? I do a little bit of lit review on simulation and experiments because it's the first few slides that I shared from Dr. Oliva mentioned that simulation is going to really be and solidify itself as a third pillar of science. It's got to be just as rigorous and reputable as any other experimental design. And so, I do a brief lit review on that. So even if you don't care about any of the tests or the model application or anything, you could still mine the background stuff here, because I cite anything and everything that I've read on simulation experiments. The paper demonstrates these tests that I'll overview in just a moment on a well-known ecological model used for teaching that comes from this book, Ecology and Natural Resource Management, Systems Analysis and Simulation. And it just so happens that Grant, the lead author there, is also at Texas A&M College Station, a colleague of Rogelio Oliva, but has done most of his work in ecological modeling using system dynamics, but not in the system dynamics community. And so here's sort of a high-level schematic of the model that's in the paper. Essentially, let me tell you the high-level story. The high-level story is there's a wildlife refuge, which is the bottom right down here, the ecosystem plants and native animals that are in this symbiotic relationship. They're in balance, not anything unusual there. But what happens is the water source that this refuge is reliant upon is now going to also support crop production. So there's going to be irrigation to support crops, and that consumption of water is going to take away water from the refuge. So that's the basic story and premise of the problem that led to the model. This is the original model boundary that's in Grant's paper, or excuse me, his book. And it does some interesting things, but I extended it to include the two reinforcing loops on top and the balancing loop B2 there on the bottom to make it even more dynamic. So essentially, as the crop production takes place, there's profitability from that, and that then reinforces the more planting and more irrigation to drive water diversion. So that's kind of a couple of reinforcing loops. And then I added this balancing loop on the bottom so that as the refuge is under pressure, there's work by conservation groups to minimize the diversion, to offset the water allocated to agriculture. So I just added those outside loops to make it more feedback rich and make it more interesting. So the paper outlines some successful tests that failed, and tests that necessitated revising our own mental models. And it does include the model and all the supporting documents, but I had to asterisk this because in preparation for this talk, I discovered that the model that was uploaded in the supplementary material that you can go download was this model right here, the conceptual VinSim, not the actual working VinSim. And so I've communicated with the journal, with the publisher, and they have the correct model, and probably this time next week for sure they'll have it up there. But if you want to get the paper and want to get the model, I can also share it as well. But anyways, that will be updated on the website. So finally, what tests do? I moved from novice test to more advanced test in the bulk of the paper. So starting with more novice, extreme conditions. So I discussed for the beginner the considerations for identifying parameters in their ranges to do extreme conditions tests. I'm kind of going to fly by these because a lot of us are familiar with most of these, I think. So that's more of a novice one. More intermediate, I do a whole barrage of intermediate type tests to develop system understanding. And so let me just define what that is first. So there's kind of the surface level system understanding that a beginner has, like what are the key stocks and flows? What are the key feedback loops you've tried to build into the model? That's kind of the surface level system understanding. What I define, or what I call the depth of system understanding, is how does that stock flow structure respond to all these changes that might take place? So, what are the range of behavior modes that model can express? That's kind of depth of system understanding. So, I do a step, a pulse, a ramp, multivariate sensitivity, a lookup table sensitivity, and behavior pattern measures analysis. And so I walk the reader through how to interpret different perturbations from the step, pulse, or ramp functions, how to do statistical screening from multivariate sensitivity, what you have to do to expand a lookup table to be able to do sensitivity analysis sort of more scientifically on a lookup table, and then what auxiliaries do you need to build in mathematically so that you have an indicator variable that alerts you to when a behavior pattern has changed in the particular variable that you care about. So those are the more intermediate ones, and then the more advanced ones are really evaluating. This is more the real laboratory stuff here, testing different decision strategies or policies. So I do 3 different kinds of what-if experiments. Um, I do a boundary adequacy test. There's also a failed boundary adequacy test in the appendix. So there's 2 of those. And then intervention thresholds, which is there's a proposed policy. How do I know how much of that policy to do and by what time to make it effective? And so there's a intervention analysis there. And so I walk the reader through the design and interpretation of what ifs and intuiting a range of high leverage policy versus low leverage policy and the simulation evidence that supports delineating those. The model structure alterations for boundary adequacy. Again, there's a good one and then there's a failed one. Or I should say a ghost one because it's not really boundary adequacy, but sometimes we think it is. And then there's a full factorial experiment for intervention analysis right there. So when I said earlier that I can't email you the paper, ask for it on ResearchGate or get it through the journal or whatever, that's why. I mean, there's a lot in here in the paper and the appendix and all the stuff that I walk the reader through. It's quite heavy. Now, hopefully it's digestible, and I've gotten some feedback so far that it is fairly digestible. So even if you don't want to go through the whole thing, my goal is that it's at least a great resource so that when you're scratching your head about lookup table sensitivity, oh, let me just go to that section and here's the model and here's the auxiliaries I have to build, and then you keep moving forward. So hopefully it's a reference like that as well. Some contributions that I think it makes is providing learners with the examples of a moderately complex model that when you go into it, you don't know the dynamics of. Not even I knew the range of behavior modes that this model could express until after going through this barrage of tests. And it's of the size and scale that most of us are probably building for our project. So it's not, a simple, one-page project model or the, SRI or some adoption diffusion model that we understand the dynamics of really well and can package that, down into a really small model. It's a model that is sizable enough that we're probably working on that scale of a model in our own projects. Another contribution that's kind of in the front matter, I think, is that it summarizes the purpose and rationale of each experiment, which are known. Those are in a lot of our literature already. But what I've added to it are the common obstacles, barriers, and limitations encountered in running each one of those tests. From, a novice is going to hang up here. For example, the extreme conditions test. Well, for a novice, it's what the heck variables are the best ones to use for extreme conditions, and how do I know what range to put on there? But for an advanced modeler, like probably a lot of us are, extreme conditions is nice, but it's really just a confirmation check of what we know the model should do. It really doesn't give us a whole lot of insight other than just checking that, things are holding up in the model the way we expect. And I do that for all these tests down for novice to advanced skill levels. And then finally, it demonstrates model testing and subsequent revisions when the model failed. So in the paper, it shows like these successful tests. In the appendix, I have how they failed before, including how one test was a pass, but we had to revise our mental model. And so that I think is kind of interesting. Finally, here in the last couple of minutes, because I think it's already about 40 minutes or so I've been walking through this. So future model applications with this. And this is where I'd like to throw this open to the floor and would be very welcoming of comments, questions, ideas, collaboration potential on this application here that I've been working on. So using this model as a learning laboratory. So so I walked through all the tests and everything, but the model, I used the model not for the paper. I actually used the model first in my classes. And what I do in my classes, I call the irrigation versus wildlife case. And it's a role-playing game that I use in my classes. So I have all this case study material that I put together that frames the issue, and water is going to be diverted, and here's, it supports this refuge, and here's the population dynamics, and here's what the irrigators are going to do, and how much do they want, and when are they going to take the water, and all this stuff is background material for the problem. I then split the students up into groups of competing, I call them consulting firms, that are hired by the watershed group, that are made up by these conservation and ag stakeholders. And I give them this challenge to design appropriate intervention strategies that will both support water for agriculture without collapsing the wildlife refuge. So what's the leverage point? What's the feasible alteration to the system that will support both user groups, both support the refuge and water for ag? So if you get the model from me or next week and they update the website and you get the model, I already have in there this interface, send to sim interface in the VinSim model that you use, and I use it in my class. And so I walk through for the students what these different sliders mean, why are they important for the wildlife population, or why are they important for the ag considerations. And I give them the ranges that those parameters can take. And then I let them go, and I give them 2 or 3 rounds to come up with their own suggestions about what parameters should change and what values should they take. I then plug them into VinSim, and they can see what happens with their proposed strategy. And then probably my experience, probably 80–90% of the time, they don't find a solution. About maybe 10 to 15% of the time, one group will find a solution that gets you pretty close. I then walk through the debrief, and essentially what happens is, because of the feedback processes at work, we either strengthen this R loop and the agriculture takes off and the wildlife refuge collapses, or we manipulate the system that we strengthen the B loop on the bottom, which is conservation of water for the refuge. We strengthen that one so much it doesn't let the irrigation take off, and then the irrigation thing becomes an economic collapse, which is not good either. So it's very difficult to strike a balance there depending on which parameters you push and how far. Now, I do it as sim to sim, and I give the students several rounds to come up with some suggestions. The next step for me, and I haven't done this, and there's sample size considerations here, is gaming application for repeated decisions, so that they run the model sequentially in time to give their policies some time to work. They respond to whether it's working or not. They might change things, rather than the way I'm doing it now, where they just suggest something, I put it in sim to sim, and they see what happens. So the gaming application is much more dynamic and can capture a lot more learning benefit and gain that way. And so that's something I would be interested in with help as a collaborative potential, as well as doing this elsewhere, because I use this only a couple of times a year in my class. And so it's really hard to generate sample size to be able to do something with, scientifically interesting. But if there are 2 or 3 of us that wanted to try this in different classes and different events, then I think we could learn some interesting things. Lastly, I acknowledge the mentors that I had, that in my own self-teaching, some of these names you'll recognize, I think. And then over this past year, to help me finish, to give me the time to finish some of this stuff, some funding support. But with that, hopefully that was efficient enough and interesting enough to keep everyone awake and alert wherever you may be. And so thanks for your attention, and open to any question, any discussion about it, more about the test. I've got all the tests on here on slides below this slide if you wanted to look at something specific there. So whatever time we have left, I'll hang out. Let's discuss any ideas. So thanks for your time.